So today we discuss potential due to continuous charge distribution. So continuation of electrostatic potential chapter. Now today's topic is potential due to a continuous charge distribution. Potential due to a charge distribution. The continuous charge distribution. Here the first we discuss a line charge distribution actually. So consider suppose a line, this is a rod, okay, and these line contain a charges, okay, and this rod, obviously a rod line continuous of charges, that is a x direction, and suppose calculate electric potential at point P here, calculate Vp, and the distance is from P to rod is D, rod is D, okay, and consider from a small length, this is a continuous charge, here the charge, okay, suppose there is small length, consider this, that is called dx, small length is dx, okay, and charge rod, small element on the particle, that is a dx. So the distance from here to at that point is x, and the length of rod, suppose here, suppose length of rod from not here actually, length of rod is L, that is the x direction, okay, rod is L. So the small element ds, so line charge distribution, you know that, so line charge distribution, okay, that is a lambda, that is equal to dq by dl, dq by dl, or dq, that is equal to lambda dl, okay, and here the length, consider small length, that is a dx. If you all say that, that is dq lambda dx, and the distance from P to dx, that length is r. So potential, suppose consider the angle is now 90 degree. So calculate potential, okay, dV, that is, you know that 1 over 4 pi epsilon naught dq over r, okay, a uniformly charged rod, that is a uniformly charged rod, okay, and produce a electric potential, if that is charged rod, produce a electric potential and calculate potential at point P, produce and produce potential calculate potential at point P. Now calculate potential at point P and choose an arbitrary element dx, choose an arbitrary element of the length rod is dx, okay, and this rod also as treated as a particle, okay, and very important point, okay, an arbitrary element arbitrary element and can be treated as a particle as particles, like charged particles. Okay. So potential set up here in sounding. Now choose any arbitrary point P, calculate for a potential at point P, the distance point P from arbitrary length, or choose that arbitrary point is actually here, that is R. Okay. So now dq, that is replaced by lambda dx, that is equal to 1 over 4 pi epsilon naught, and dq replaced by lambda dx over r. So now replaced by r. So what is the value of r here? So if you see the carefully the diagram, that diagram actually show that is a right angle triangle ABC. This angle 90 degree. So R is the hypotenuse, D is perpendicular, X is the base. So that is equal to 1 over 4 pi epsilon naught lambda dx, that is R equal to root over of x square plus d square dv. Okay. Now calculate potential. Now integrate both sides. So here, so next page. So integrate dv. We get v, and the integrate obviously 1 over 4 pi epsilon naught is constant outside the integration. That's why. So lambda dx by root over of x square plus d square. So the limit is from 0, there is the origin 0 to that length is L. Is 0 to L. From 0 0 to 0, actually 0 L. L 0. X equal to L or Y equal to 0. So 0 to L. Now solve this 1 over 4 pi epsilon naught lambda outside the integration. So dx over x square plus d square whole to the power half. Okay, that's actually easy to solve this. That is a log value lambda over 4 pi epsilon naught, that is ln, and x square, the different integration of x square, if I goes to that is x minus 1, so that is 1 by x, so ln x, and here this term, that is ln x square plus d square whole to the power half, and the limit is 0 to L. Now lambda over 4 pi epsilon naught. Okay, so put the limit x ln, sorry, curly bracket put here, L plus L square plus d square whole to the power half minus ln, put 0 0 ln, so here we get a d only, ln d. So next line, lambda over 4 pi epsilon naught. So ln log a minus log b, that is equal to log a by b. So ln natural log L plus L square plus d square whole to the power half by d. That's the potential at point P. Okay, so box that. That's the potential at point P in that produce an electric field when uniformly charged rod, that electric produced by the uniformly charged rod. Okay, that derivation is very important for board exam. Okay, very important. So practice 2 or 3 times and easy. Okay, nothing worry about. So now next calculation is a calculate magnitude of the electric potential at a point from the central axis of a plastic disc of radius r. So calculate potential 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 of a point on a central axis. Okay, potential at a point on a central axis of a plastic disc. Okay. Plastic disc of radius r. So if we choose a plastic disc, now look like this. So okay, now choose inside a length. Okay, inside the thickness. Okay, choose that thicker part of inside thickness. Okay, thickness is dr. The thickness is dr, and the radius of the disc that is r, and if that is thickness is also that is a dr, the central point. So potential at a point on the central axis. So here we get a central axis. Check mode. Okay. So calculate potential at point P, and suppose Vp. So choose that is called R from dr length, that is also dr, this gap, and that radius is r dash. Okay, and that length is z. So calculate Vp of z actually. So calculate potential P, the function is z, right, for charge distribution of a circular disc. Of charge distribution of a disk. So here with dq, the charge distribution here, that is surface actually. These are the surface. So it came from sigma, and it is area. Okay, the disk area is the boundary. Okay, circumference that is into 2 pi r. Suppose, okay, 2 pi. The distance is r dash. Okay, times the thickness times dr. Okay, so you get the area. That's so you get some area actually. So that is sigma, the surface charge distribution, that is equal to total charge by area. If I this the by area, and that is sigma equal to dq over dA area. Okay, surface charge distribution. So potential at point P we get 1 over 4 pi epsilon naught fixed value, that is dq over r. So that is dq, so dvp here. So integration of v dv, sorry, integration we get v. Dv get v, that is 1 over 4 pi epsilon naught sigma 2 pi r dash dr dash over the r. Similarly, the triangle is the right angle triangle, so that is r is the hypotenuse. So r dash square plus z square integration. The integration limit is 0 to capital R, from 0 to that the limit actually. The limit signifies that actually where we can choose this arbitrary length. Okay, arbitrary actually the area of this. So a small area of that arbitrary area. Either here, anywhere. That is 0 to R. Okay. Now we solve that B equal to 1, sorry, sigma outside. Okay, that is sigma times 2 pi by 4 pi epsilon naught 0 to R dash dr dash over z square plus r dash square whole to sorry here the whole root. Okay, because the hypotenuse square equal to base square plus perpendicular square. How? Okay, now solve this integral with very easy way. Now let assumption say that is equal to say that z square plus r dash square we put that is equal to a. So differentiate to r dash dr dash that is equal to that is a square 2a dA, a 2 cancel. So r dash dr dash that is equal to a dA. Now put that here that is equal to, so cancel these 2 by 2. So sigma by twice epsilon naught 0 to r dr dash we replace by a dA. Okay, and that is equal to a square times half, gets only a, cancel these two. So sigma by 2 epsilon naught, integration of dA is a, 0 to r. That is sigma by twice a, now, twice epsilon naught. Now a that is equal to this root z square plus r dash square, okay, root 0 to r. Now put the limit, we get a final answer. So potential at point P, sigma over twice epsilon naught, okay, z square plus r square, okay, first term minus all value put here, so that is minus z. Okay, that is the final value of that equation, the Vp, potential at point P on charge disk. Okay, easy to calculation, that's not tough. Okay, integration also be the very easy. Clear? Suppose that is a plastic disk, so plastic disk contain positive charge. So here the plastic disk at radius r, charge on the disk is top surface and that is a uniform surface, this charge density is sigma. So we say we wish to find the potential V at point P on the central axis of the disk. So here conclusion, a plastic disk, a plastic disk, okay, at radius r, the radius is r, we see that this is r, radius r, okay, charge on its top surface, on its top surface, okay, to a uniform surface charge density. Uh, charge density sigma dot. So we wish to find a potential at point P. So potential at point P on central axis. That's the central axis. Central axis means the passes that line to the center of the disk circle. So that axis is called central axis. Okay, this axis is called central axis. Okay, very easy to calculation. Okay, the very easy. Okay, do not. So as a practice 1 to 2 times and easy. Okay, the derivation is very important. Okay, so next topic we discuss important conceptual topic, calculating field from the potential. Calculating field from the potential. calculating field from the potential. So you choose an potential surface, like these are the potential surface. Okay, these are the equipotential surface. These two are that equipotential surface. Potential surface. Okay, these are the equipotential surface, and we move a test charge in that direction. A positive test charge Q naught. Okay, move in that direction. Okay, that is a ds vector, and the electric field, that is suppose that electric field in that direction, actually piercing the surface. Okay, piercing that angle is 90 degree, piercing the surface and up down, up from the boat. Okay, that's the point P. Piercing the surface, actually that is a perpendicular to the surface, equipotential surface. E is the perpendicular to the equipotential surface. Okay, so if that suppose, so we say that, or if I choose any value of theta, actually that not actually here you get not a piercing, they are actually piercing, but the angle is not 90 degree. Okay, suppose the angle is maybe the theta. So component of E along the ds, charge moving from suppose here to there, so that is the E cos theta. So that is vector component part. Okay, that is an easy topic. That is equal to E hypotenuse, that is a base. A relation between base and hypotenuse is a cos theta. So that's a very important concept. So the test charge moved to a displacement ds direction. So test charge Q naught moved in the displacement ds direction. If you know that the potential V, that is equipotential, same potential. So near the assemble of all charges to draw in a firmly a equipotential surface. So that's the potential value the same. So draw that line. So you get equipotential surface. And the electric field lines scales the perpendicular to the surface. So electric field lines scales that perpendicular to that surface. And what we are seeking here is that the mathematical equivalent of the graphical procedure. We see that, actually know that what is graphical procedure. Here there are cross section of the firmly you choose the placed on equipotential surface. Is the equipotential surface. The potential difference between each pair of adjacent surface, is dV. Okay, each pair of adjacent surface is dV. Suppose the dV, the potential difference dV in figure suggests the field at any point at P, okay, is perpendicular to the surface through P. Okay, to the surface through P. They're very important. But we choose that any arbitrary point. Okay, that's the annual theta value. So here the test charge moves through the displacement ds from that point to here I to F, displacement from that equipotential surface to another adjacent equipotential surface. So here are the two types of work done by the test charge and work done by the field. So write the note of that points. If you write to note in your own words, that's very good. Otherwise, pause the video and write down the note for understanding, for better understanding that. The test charge moves through a test charge through a displacement ds vector ds vector. Okay, if you know the potential V at all points, so if you know the potential V at all points, the potential V at all points, near the assemble of charge, the assemble of charge can draw firmly in equipotential surface. Can draw equipotential surface. Okay. So electric field line. So the electric field line lines. Okay. Perpendicular to those surface. Perpendicular to those surface. In figure, this diagram, the cross section of the firmly closely spaced equipotential surface, there is closely spaced equipotential surface. The potential difference between each pair of adjacent surface is dV. Suppose that is the potential of each pair is gap between these two potential is dV. The potential difference between two adjacent surface, the surface equipotential surface is dV. So figure any point perpendicular to the surface. Figure P any point that is perpendicular to the surface. So here the test charge moves through the displacement ds vector from an equipotential surface, one surface to another surface. Okay. So work done by the test charge. Here two type of work done. Work done by the test charge. Work done by the test charge, that is equal to, so work done by the test charge, that is equal to work done by the electric field. Work done by the electric field. By the electric field. So work done by the test charge, we know that that is very easy. That is minus Q naught times dV in terms of potential, and work done by the electric field, that is a important E term. So here we get dV, that is E dot ds, and that component E, test charge move, component E, that is equal to E cos theta along the ds axis times ds, or the dot product is E ds cos theta. Okay. So cancel these two. So we get a E cos theta, that is equal to minus dV by ds. Okay. So if we terms as a partial derivative, we get a Es, that is equal to, so partial from 3 axial xyz, that is delta V over delta S. Okay. So see the carefully, the cos theta is removed. Why? Because that is E cos theta, that is a component. Okay. So here that is E cos theta, that is equal to Es. Okay. That's the ignore. That is a partial derivative, and that is E is the any direction, that is a negative direction, that is very important. Direction is the negative direction of the rate at which the electric potential charges with the distance in that direction. Okay. So here the component of E, the component of E in any direction, in any direction, in any direction, okay, is the negative of the rate, is the negative of the rate, of the rate at which the electric potential uh, electric potential changes with the distance in the direction. Changes with the distance in the direction. Okay. Suppose that is an Ex, that is minus del V by del X. Suppose the Ey minus del V by del Y, Ez minus del V by del Z in X, Y, Z direction. Okay. So potential of V, X, Y, Z. So we get finally in terms of representative E equal to minus del V by del S. Okay, if you know the V for all point in the region and the charge distribution like a V, X, Y, Z component, we can find the component of E. Then E is also itself at any point by the taking a partial derivative. Okay, if you know that all point of V value, so you take a partial derivative, you get a final value answer. Okay, so today I end the class here. If any doubt about what is the electric field and potential, how to calculate the work done by the test charge, or here the calculating field by the potential, if any doubt on that, and there's an important calculation in board exam, because that calculating potential of central axis of the plastic disc of radius are, that's very important for board exam. Similar like these, the derivation is, these two derivation is very important, okay, in board exam. So today end the class here. Thank you.